Okay, so what I'm going to do is try to give you a walkthrough example of the data screening using the master pill file that I gave you in class. And so you can listen and watch the video to be able to help you with your homework. All right, so I have this data here, and it's 20 questions of a 1 to 7 Likert scale that we use to test students' purpose in life. I also have 2 variables that tell me where the data set came from, which we're not going to use for data screening, but it's a really good example of a categorical variable that you wouldn't screen. So remember, you don't want to screen your experiment variable. If you put them into groups or gender or religion or things that just are. So we really want to screen the variables that are given to us that are usually sort of continuous in nature. The other one we have is a string, which is our ID code, so I'm not going to use that one either. So I'm going to leave these first 2 alone and work on the bottom 20 questions for this data set. So the first thing you really want to look for is accuracy errors. So things that are incorrect, that are out of range, or maybe they just look funny, so you can look at them again later. So a lot of this first step ends up being really just to see what else you might need to check. So in looking at this data, I clearly have some people who didn't actually take the study, or they opened the study and never completed this survey. So at some point I'm going to clear those out as well, but I'm going to do that in step 2 under missing data instead. So to check for accuracy, I'm going to go to Analyze, and then Descriptive Statistics, because we're looking at the descriptives first. And then I really like frequencies. There's nothing wrong with descriptives, just frequencies gives you more options. Analyze, Descriptive Statistics, Frequencies. I'm going to ignore my first 2 variables because, again, I'm not screening those. And I want to move over all of them. Now, one thing you could do is if you have a gender variable or you have religion or ethnicity, you probably do want to screen those to make sure that it doesn't have any weird codes in it. So like if you accidentally hit 7 and you meant to hit 4, or you have a 0 in a gender and everybody else is 1 and 2, that sort of thing. So in this step, you do kind of want to screen those. So I'm going to make sure my source variable doesn't have anything other than 0s and 1s in it, because that's the codes we use. All right, and under statistics, I'm going to ask for the mean, so I want an average score, but mostly this is about min and max. So can I get the minimum and maximum to make sure they're in the right places? I'm going to ask for the standard deviation. You can look at skew and kurtosis to make sure they're not too crazy. But remember, if you have an outlier, your skew and kurtosis might be very high, and then you might fix that in step 3. So while I'm going to look at it, I may not necessarily have any problems that I can fix right now. I hit continue. If you wanted to look at all the charts, you could hit charts and then do histograms, and then hit continue. But if I do histograms, I'm definitely turning off frequency tables, so I don't get 87 pages of output. That's up to you at this step, because we're not doing normality yet, but sometimes I'll click all the buttons just so I have it later. All right, so I'm going to hit OK. So from here, I have a gigantic box, and I'm going to really start by looking for out-of-range scores, because it's the most problematic thing that we can start with. So if you're looking at the handout for this, I'm under accuracy, and I'm on B, so I'm going to fix those out-of-range scores. I'm going to look here at min and max and just kind of scroll across and make sure nothing is out 0 or 8 or 12. And since this data came from an online piece of software, it shouldn't have any errors, and it doesn't. Now we added the source code, so I want to make sure that it doesn't have a 2 or 4, and it doesn't seem to. But one problem that you'll have is that if it had a 0.5 by accident, I won't know here. And so I can scroll down to look at the histogram, so I'm going to click over here to go there quickly. And it looks like it's all 1s and 2s. So it centered it over, I'm sorry, 0s and 1s. So it centered it over 0 and 1, so I don't have anything weird going on at 0.5. So going back to the statistics, I don't have any out-of-range scores, so I'm okay. Now I can look at my means and see what kind of scores I'm getting. So I have some really low numbers, 3.24, and some really high numbers, 5.6, and then a 1.89 on this retirement question. And if you're working with a scale, that's a really good sign that maybe you forgot to reverse code something. So it looks to me like some of these didn't get reverse coded, and I know they haven't. So that might be a good cue to like go, oh no, these all should be high numbers. I forgot to fix this. And then in looking at the standard deviations, they're all pretty normal. I got some almost 2-point standard deviations, but I know those are normal because these are weird questions because they're asking freshmen in college about how they feel about death and suicide, which usually gives you some pretty wild answers. But the rest of them are pretty normal. So I don't have any standard deviations that are too big for a 1 to 7 scale. So 1 to 2 points is pretty normal. You can also check out skew and kurtosis. Be sure you look at the actual skew line and not the standard error line. And they're all looking pretty good. So remember, 3 is the cutoff for skew and kurtosis. And that's the absolute value. So I don't have any problems here. All right. So I've worked through accuracy, and it doesn't look like I have any issues. Check. Now, if I did have issues and I had deleted some data points, then I would want to rerun this analysis to fix my missing data. So remember, if you delete data points, individual points that are incorrect, you now have missing data that you don't see in this box. I didn't delete anything, so I'm going to look at my missing data, and it's right here, so I can run the same analysis. And I'm going to look, and I do have a lot of missing data, 60 points in each line, but remember we've got some data that's just people didn't take it. And then our very bad question where we have left out the question for the first 300 people that we ran, so that's missing not at random. It is a experimenter error. Let me go back to the data and see what's going on with this missing data. If you want to do this quickly, remember you can hit this little star go to data button. All right. So clearly have some data that is just dots here. That's my missing data. And it's people that have just not finished the survey. So I'm going to right-click on the column and do sort ascending to bring all those people to the top. And so the ones that are totally blank are just, they didn't even see it probably. So I'm going to delete those. But I also have this sort of problem where I have people who half took the survey. So they took the last like 6 questions. Now to me, I don't want those people because they didn't complete it. And remember, for missing data, you have to fill in less than 5% going across or 5% going down. And that is way more than 5%. So I'm actually going to delete these people too, because I don't want to fill in most of their data. That would be like making up an entire participant score, and that's not a good idea. So I'm going to delete them too. Now this person that popped up to the top is only missing 1 data point that they skipped, and we're like 1 data point that sort of was my fault. So I'm going to leave them in because 2 points on their scale is not a bad number to estimate. Let me get rid of these. So this other person I brought to the top is only missing 1. They skipped question 1. And then I'm going to get rid of these. I'll do that for a couple of questions here so you can kind of see where the missing data is. To get out to that, how do I know if it's mnar, not at random, or mcar, at random? Well, if you're sorting these variables and there's only a couple little data points and there's not like a big block of missing text, then it's completely at random, which is what you want. You want it to be random. So here's another example of a participant that took the first several questions and then didn't do anything else, so I'm going to get rid of them too. And then if you sort down here at the end, you can see an example of this is not at random. So when I have this many missing data points for 1 column, something happened. And I know what it was. We left the question off. But if you didn't know why they had skipped it, you'd want to figure it out. Maybe it was miscoded in your survey program. Maybe you left it out. Maybe it's a question that no one wants to answer. Maybe they feel like it doesn't apply to them. So this is where it becomes like an interesting question to figure out why. But for the rest of these, it's pretty much at random. It's like every once in a while they skip a question because it's an online survey and that's easy to do. So I feel pretty comfortable filling those in. I'm going to rerun my descriptives, so analyze descriptives, frequencies, and just to make sure that my missing data isn't too much. Now, after I've cleared out all those bad people, I have 2, 5, 4, 3, 1, that's got 9, but that's all way less than 5% for any given column, because 5% would be like 50 or more people in this data set. Now, with this one particular question, the death question, it is more than 5%, so I don't want to fill that one in. So I'm going to leave that one out of my mean replacement, my linear trend at point replacement. So what type of missing data do I have? I have both. I have missing completely at random, that's the good stuff, and missing not at random because I screwed it up. And I'm going to fix the data. Okay, there's a couple of options that are reasonable. You can fill in data that's missing completely at random with linear trend at point in SPSS. You can not fill in any data. That's an option too, but definitely don't fill in the data that's missing not at random. So this death question. So I wanted to do that. I would go to transform and then replace missing values. Now the tricky part about this window is it always is on series mean here. You want to change that before you do anything else. This is the only window like this. So I'm going to change it to linear trend at point to start. If you don't, what you'll see is it says S mean here. You don't want that. You want it to say trend. So I'll back this one out, change it to trend. Now I don't want to fill in my source data because that's just my experiment column. I'm going to pick all the other questions here and move them over. Now I'm going to go in and find that question that I don't want to fill in, which is I know is number 45. So I'm not going to fill that one in. That's my death question. Because it's not at random. I want to fill in the completely randoms, but not fill in the not at random ones. So I don't want to fill in my mistake. I'm going to hit OK. And it gives me a box telling me how many it replaced. Now, if I had moved over columns that didn't have any missing data, it just leaves the column alone and fills in that same column in a new place for you. And so these numbers will be 0, and that's perfectly okay. Let me go back to the data here. That I should have all new columns where those numbers are filled in. Now, one thing I would do here, if this were my own data set I was working with, I would save this as a new file. So I had a sort of a no missing file, and then I would get rid of all these other variables. That's what I'm going to do. I'm not going to delete 45 because I need it. I'm going to stick 45 where it should go down here between 44 and 46 and get rid of the rest. All right, let me say that here. So I would save it as pill no missing. My SPSS does this fun thing sometimes where it doesn't like the first letter, so that's just my computer being weird. So what does that do for me? What that does is it gives me a data set where all of the things have been fixed on this particular set of steps, accuracy and missing, where I don't have all the other variables. So I'm not tempted to use columns that I haven't fixed. So if you have multiple of the same columns, what happens is the ones that are unfixed are at the top, and it's really tempting to just use them again. And so what you'll see when you run Outliers here in a minute is that you'll be tempted to pick those, and then you'll get missing data points in your Mahalanobis, and you won't know why. And that's because they have missing data. So when you start to screen for outliers, anyone who has missing data just gets ignored, because generally they're going to be ignored in your analysis too. So you'll see that here in a minute when we do for question 45. You'll see that these people won't get an outlier score because they don't have all the questions you're interested in. So I would save it as a new data set just to make my life easier. But always keep your old data sets. So when someone asks you, how many people did you delete for missing data, you've got that original data set and your new data set, and you could just compare how many lines they have in them. So how many participants are in each one. All right, and so moving on to outliers, I have you doing both the univariate and the multivariate calculations. The further we go, the less you'll do the univariate, but for right now, it's just a little bit of practice. And so with outliers, I'm really looking for people's scores who are crazy. And in a univariate way, I'm doing that to look at individual scores on a particular column. So if you're really interested in one variable, univariate, multivariate will give you the same answer. But since I actually have 20 variables, I really want to know if their score is completely nuts across lots of things. So is their pattern of scores unexpected? To me, that's much more interesting because then I can say, well, I'm going to delete them because they clearly weren't taking the survey correctly, so they filled it in with kind of a goofy pattern because they were bored, or because maybe those scores really are kind of nuts. Now, for the reverse coding thing, when I said I hadn't done that a minute ago, it doesn't really matter when you're doing data screening because it doesn't, like just transforming the scores from 1 to 7 to 7 to 1 don't make a difference. But when you get to actual analysis, it does. So I always tell people to do reverse coding at the beginning. But since I'm just doing data screening, I'm not going to do it on this data set. All right, so let's work on outliers. So for univariate outliers, I'm just going to create a couple of them. And that is under Analyze, Descriptives, and then Descriptives. So this is the only reason I ever use the Descriptives window. And let's pick a couple of little variables here, move them over, and then click Save Standardized Values as Variables. In the Windows version of SPSS, the Z is underlined to remind you this is Z scores. In the Mac version, they're not that cute, so it's not there. And then hit OK. So I've created Z scores for my continuous variables. The next question on the handout here is, what's the Z-score cutoff for univariate outliers? That is always negative and positive 3. That one doesn't change. So you need to look at both ends, the top and the bottom of the data set. And let me go back to my data here. There's two ways to do this. If there's just a couple of variables, just sort each variable. So descending, there's nobody at the top. Ascending, we've got some people close at the bottom, but they don't cross 3, so they're okay. Nobody here. Nobody here. Oh, here's some outliers. So we got some people down here who are over 3. So we got 3.29, so 20 data points here on this question that are significantly lower than everybody else because it's at the it's a negative score, so it's at the bottom of the data set. And then if I sort the other way, I don't have anybody at the top. Sometimes I'm interested in, like, why are they so low? Resort it here. What I might do is, this is question 33, is go back over here to question 33 and figure out why are their scores so low. Well, the average score for this question is probably pretty high. You could go back and look at that. And these are people who marked 1 and 2. So those are valid scores, it's just that they're very low. So sometimes univariate outliers are not the best thing to look at because these are valid scores. They're perfectly reasonable things to mark on a 1 to 7 scale. It's just that everybody else is so high, you've got just the tail end of the distribution here. So you're just looking at a couple people. So one of the reasons I promote multivariate outliers, especially on scale data, is that it really ignores the fact that every once in a while somebody just marks a low score on something and looks at all the scores at once as opposed to one little score at a time. But we do have some univariate outliers. A faster way to do this for multiple columns is to go back and do Analyze, Descriptive, and then Frequencies. I'm going to hit Reset to clear everything out. But I would do a frequency analysis for my new Z-score variables. Okay, so what does that mean? I'm going to hit Statistics. I really just want the min and max. Okay, I don't even mean it's going to be 0 because this is a Z-score. Remember the mean of Z-score is a 0. And then I'm going to turn off frequency tables because they get on my nerves. So I'm going to hit OK. what that does down here at the bottom is it tells me the highest and the lowest score for each column, and I could pick which columns have the bad scores and go look at those. So I could tell that these first two columns were okay, and that this last column was the one I needed to go look at because it's got clearly a score lower than -3. That's kind of a faster way to do it if you have lots and lots of columns for univariate outliers. All right. In the next video, I will talk about multivariate outliers and then keep going through the rest of the data set: multicollinearity, normality, linearity, homogeneity, homoscedasticity. With a reminder that on all of these analyses, they will change slightly depending on what type of hypothesis testing you're doing. So data screening always comes first, and it is just a check. Am I putting garbage into the data set, or am I running something that looks like it's pretty reasonable? And then there's hypothesis testing. So you have to match the two. So sometimes multicollinearity just doesn't work because you don't have enough variables for that. So when we do the rest of this data screening, remember that there are lots of times when you won't use some of these. And for each analysis we'll go through in the rest of the class, we'll talk about when you would use each one. Okay, so I'm back, and now we're going to do multivariate outliers and the rest. So we just finished univariate outliers, and I looked at each individual data point, and now I want to calculate how many times things are multivariate outliers, because I have multiple columns I'm interested in, and this is much more efficient. And so I usually will ask you to include the top 5 Mahalanobis scores, so just give me the top highest people to make sure that you're on the right track. And if you aren't on the right track, we can know where the rest of your answers are going. So in all of these assignments, if you miss a step, clearly it influences the next couple of steps. And by including all of these pictures as part of your assignment that you turn in, that really helps me know, 1, where you've messed up and to let you know, but 2, like how you got the answers you did. Okay. So I am on the handout on 3B for multivariate outliers. And to start, I need a random variable. So we talked about in class that we want the errors for our variables to be randomly distributed. So we're going to compare our data to a random number so that we can show that they're randomly distributed. Now that really matters more for normality and homogeneity and homoscedasticity. But for multivariate outliers, essentially what we're doing is we're testing if their set of scores is the same as the average set of scores. So it takes an average of all the scores and sort of plots it. So I have the middle of the middle. And when we have 20 scores, that means it's the middle of 20 of them in like 20D space. And so then it calculates how far away each person's individual set of scores is. So it's actually a Euclidean distance measure, which is sort of like a hypotenuse on a triangle. So how far away is their set of pattern of scores from the average pattern of scores? And if they are very far away, then that means that their scores are kind of weird. And we calculate that against a random variable so that we can get the rest of this output to be appropriate. It actually does not matter for Mahalanobis what you calculate with, but because we use this fake regression, excuse me, to run the rest of this data, it just helps if you start with a random variable. So to do that, I'm going to go transform and then compute variable. I always call it random because then I remember what it is, but you'll want to call it something that means something to you. In this function group, what you want to do is go down to R for random variable, so I'm going to hit R on my keyboard, and it takes me down to random numbers kind of quickly. I want to use RV chi-square. So why chi-square? Well, the way Euclidean distance is calculated is that lots and lots of things should be very close to the average, and only a couple of things are going to be farther away. And if you plot the likelihood against a random number, it is the chi-square distribution. So what that means is that there are lots of variables that are very close, and then there are fewer things farther away. And if you were to make a histogram, it would look like chi-square. And so it's plotted against a random chi-square number, so to match what we're going to use as our cutoff score. So I'm going to double click on chi-square, or you can drag and drop. And now we'll stick it up here in the numeric expression box. You get a little question mark, and it's highlighted, so I'm going to hit 7. Why 7? It works well for me. Don't pick a negative number because you'll get an error. And then if you pick 1, 2, 0, 1, 2, 3, it kind of freaks out. So 7 is just been a number that's worked out really well. It's not actually random. It gives you the same set of random numbers every single time. But if we're all using 7, then we should all get approximately the same numbers, and that just helps with assignments. Okay? You don't need to do 7. You could do 35. Pick your favorite number. So I'm going to hit OK. And what that does, go back to the data here, create me a new random column out here. So I now have a random set of numbers to compare against to make sure that this data is truly random for the assumptions, and something to compare against for Mahalanobis. So I'm going to start with my outliers. So go to Analyze, Regression, and then the Linear. Okay. And I will get the linear regression box. This is a fake regression. When we get to real regression, we'll talk about what the differences are, but this is the general way that you run this. The random variable always goes in the dependence box because we're comparing against that random variable. And then I'm going to take all of my continuous measures. Okay, so I still got my z-scores out here. I could get rid of those. But I'm going to take all of my filled in data. Remember, I didn't fill in 45 because that was my mistake, and I didn't want to estimate a third of the column. And so that is 20 questions that I'm interested in screening whether or not people have crazy scores on. So I'm going to put those in my independence box. If you can't remember which is which, the easy thing is that the random variable has to go in somewhere. Otherwise, why did you create it? So I'm not going to have you do things that you aren't going to use. And there's only one spot for dependent. And I want to stick multiple variables in, so that's the only pattern that will work in SPSS. I didn't screen the source variable. That is something I gave to them. So we put people in 2 different groups. Also, don't screen gender, religion, all that kind of stuff. So those categorical variables, now we're going to leave them out. So they are not going to be included in this analysis. Under plots, I'm going to put Z predicted in Y, Z residual in X. So what's that going to give me? That's going to give me a plot of the predicted values and a plot of the residual values. So predicted values are what would I have expected your score to be if I were to use all of the scores in your data to predict a random number. So I would expect it to be random, right? I'm using your data to predict a random number. So I should just get all answers all over the place. Z residual is how different your predicted score is from your actual score. And again, this should also be random because I'm just sort of predicting this against a random set of data. So this should come out as a haphazard set of dots. Okay. They are Z-scored, so you get them around 0, which makes it much easier for you to read on the chart. I'm also going to ask for the histogram of the residuals so I can look for normality. And then the normal probability plot, which comes out on your output as the PP plot, which will let me do linearity. Okay. So this is the window we're doing assumptions in. So assumptions are multicollinearity, normality, linearity, homogeneity, and homoscedasticity. So if you're looking at this handout, it's basically 4 down. So these are things that you assume about the data set that need to be accurate for your output to be accurate. Okay, outliers, accuracy, and missing data are just problems you have to fix. These other things are technically called assumptions. And this window gives us all of them except multicollinearity. I'm going to hit continue. Under save, Since we're doing a fake regression, I'm just going to ask for Mahalanobis, which is here under distances. Once we get to real regression, we'll talk about Cooks and leverage some more. So hit continue, and then OK. I'm going to get a bunch of output, but for right now, I'm going to ignore it because I'm interested in outliers, and this is the next step. I'm going to hit the star button, go back to the data. And so you'll see that there are several holes here. So that you didn't do anything wrong. That's supposed to happen. And it's the same lineup as where there are holes in this 45 question. You see there's a missing spot here under 45. And then over here, there's a missing spot under Mahalanobis. If I was to sort ascending, you will see all the missing data lines up with that question. So anyone who has missing data that you didn't fix for whatever reason will not be screened as part of the outliers. Why? Well, if they have missing data and you're going to use that column in your analysis, they're going to get left out of the analysis because their data is missing. And so it leaves them out of this analysis too, because if they're not going to get used later, I don't need to screen them for outliers now. And so sometimes what you'll have to do is screen for outliers for different tests differently. So if I am using this variable in one analysis but not another, I might have to screen it twice, once for the first analysis and once for the second analysis, because people who are missing data won't get screened in one or the other. Just sort of annoying, but that's the way it works. So I'm going to sort this column descending. So if I was to include the top 5 scores, it would be 90-ish to 118. And so when you're doing your assignment, you can just cut and paste these scores into Microsoft Word. The next question is, what is your degrees of freedom for this cutoff score? Well, the answer to that is the number of variables that you have, so we've called that K before, or the number of things you've stuck into that box for the independence. So when I went analyze, regression, linear, I put 20 variables into this box. So my degree of freedom for this analysis is 20, because I have 20 variables, I screened 20 of them, and I'm done. So my degree of freedom is 20. So what does that make my cutoff score? Let me see if it'll let me do this here. I am going to go look up a chi-square table. So you can use the one on Blackboard or you can Google it. And I want to use 0.001. So we talked about skew and kurtosis and normality, z-scores. The cutoff score was 3. Well, why is it 3? Well, for z-scores, a cutoff score of 3 is close enough to p equals 0.001. That's good enough. And so we want to use 001. This is the big important rule, and this is where it starts to matter. So I only want to take out people whose scores are 3 standard deviations away from the mean, or there are less than 1.1% of the data. And so their scores are extremely weird. So 001 for data screening, 0.05 for hypothesis testing. And so there'll be a switch. You'll do all this data screening and use 001, and then you stop. You run your real analysis, what you're actually interested in, and you use 0.05. So try to keep those straight. That's going to matter more as we get into hypothesis testing over the next couple weeks. All right, so I'm just going to go down here to 20. And so my cutoff score is this 4532. And that means everyone whose Mahalanobis score is higher than this one is an outlier. And so we're comparing our random chi-square calculated values to a chi-square distribution. So all these things come back together and they chi together. So I'm going to use that chi-square distribution because I know that random chi-square, that random distribution is chi-square. And so there is a reason for chi-square. And plus they're always positive. So I'm going to go back to, my Mahalanobis column here. I'm going to go down to 45. Keep going. So in my data set, I have 66 outliers. So there are 66 people whose scores are above a cutoff score of 4532. I mean, this person at the bottom is really close, but they're above that score. So I would say I have 66 outliers. What I could do is look at my z-score variables and see if they have a crazy z-score. So if I scroll over and look at just a couple of variables I calculated a minute ago, they do. So people who have, like this person at the bottom anyway, a Mahalanobis score over the cutoff also have a z-score above the cutoff, and that will tend to happen. So if I come up here to some of these other people, they're close to the top, but not always. So sometimes the z-scores are well within your sort of normal range, and sometimes they're not. So this is why Mahalanobis to me is much more useful, because it captures those people whose z-scores look kind of normal, but their pattern of scores is so different from the rest of everybody else that your analysis is going to suffer for it. All right, so how would I fix those outliers? There are a couple different options. If you have a big data set, just delete them. I know it feels hard to delete data that you collected and spend a lot of time on, but remember that people suck. And so sometimes they don't do your experiment the way you wanted to, or they're just not who you're intending to test, or the computer fails. So I'm in the boat. If you have a lot of people, delete them. And we have 1,500 people in this data set, so I'm going to get rid of the 66. This does not count towards that 5% rule. This is a totally different step. So sometimes people are like, oh, I'm deleting more than 5%. Totally different step. That rule no longer applies. You can also leave them in. And what I do sometimes when I run analyses for publications is I will test it with and without. So I'll try a data set with the outliers and a data set without the outliers and see what happens. Often it doesn't make a difference if you have a lot of data. If you have a smaller amount of data, sometimes one person can make a big difference. All right, so I'm going to delete these people. Highlight all of them here, hit delete. And now my Mahalanobis score is everybody's below normal. Excuse me. I am going to save this data set. If I can do this correctly, as pill no out. So now I have a master data set, a no outliers data set, a no missing data set, and a no outliers data set, so I can compare them later if I wanted to. All right, so now I'm all the way through outliers, and I've deleted people. What that means is that all of this stuff I have in my output is no longer useful, because there are people in here that I've deleted. So I might have gotten rid of this end here, or these dots out here. So don't just use the output that you have if you delete people. So that's another rule. So if you delete people, rerun it. See what happens now. Okay? So the next step I'm going to do is multicollinearity anyway, which I don't get from my fake regression. And so I'm going to create a correlation table of just the continuous variables. So remember, we're not screening categorical things. So that's under Analyze, Correlate, and then Bivariate. And I'm going to pick all of my categorical variables, which are all these trend ones, and move it over. This is going to be a giant table, so here we go. I hit OK. And it's a huge table. So what am I looking for? I'm looking, you can look below the ones or above the ones here. It's the same table. It's a same triangle on each side. I'm looking for correlations. So where it says Pearson out here, I'm looking for where it is over 0.9, positive or negative. So when variables are correlated at 0.9, that means that 81% of the variance is exactly the same. And that means they're almost the same damn column. And so you don't want to use multiple columns of the same data, because that doesn't help you any. That actually hurts you. So you run all this data and you use multiple columns that are the same, a couple things are going to happen. One of the variables is going to look bad. It's not going to do anything for you because it doesn't add anything in to the analysis. And two, you're going to lose power. So you may not find anything significant because they're so overlapping, they're sort of squishing each other out. So it's like having two loud friends in the same room. You don't understand what's going on because they're competing for attention. Okay? And that's bad for you. So you want to check and make sure that there aren't two variables that are approximately the same. If there are, just exclude one of them. And this really depends on the analysis. So out of all of these, I would say multicollinearity, which is step 4, is the one that sort of, it depends on the analysis the most. So for some things, if they aren't super correlated, you're going to have problems like factor analysis. You want those questions to be correlated. In some analyses, if they're uncorrelated, it's the best for you. Then the other analyses, if they're not correlated even a little bit, you're going to have trouble. So we'll talk about this more as we go, what exactly you want, but the general rule is 0.9 is bad. Sometimes multicollinearity is called additivity. And so additivity is good. You want that. You want each variable to add something to the analysis. Multicollinearity is bad. And so this is sort of a weird assumption because it's labeled the bad thing, where the rest of them are labeled the good thing. So I don't want multicollinearity. That's bad. I do want additivity. That's good. So I would scroll through each one of these and make sure they aren't too high. Now, this is a developed scale, so they're going to be correlated because they're all about the same topic, but I just don't want it to be over 0.9. You can cut and paste this gigantic box into Excel, if that makes your life easier, or you can double-click on it and hit Control F, or if you're on a Mac, Command F, or Apple F, is what it used to be called. And that will let you find things. So do 0.9, and then hit Find. And that will help me look for where the 0.9s are. Now, the tricky part about doing this Find option is if the sig value is 0.9, meaning they're not correlated, that's okay. So you want to make sure when you're looking for the 0.9s, you're looking at where it says Pearson correlation only and not sig. The other way to do that is from the edit window, find and table down here. So edit, find. This appears to be okay, so I'm good. Now, up until this point, we have to do them in order. Because if you have missing data, but you also have accuracy errors, and you fix the missing data first, and then you find a typo, essentially that's new missing data you have to deal with. And since the missing data is calculated based on column and row averages, that accuracy error has screwed up whatever you did first. And then if you have missing data that you don't fill in, that messes up your outliers. So you have to do it in order, and I really love to ask this question, why is there an order? Because the next step will get screwed up if we don't. All right, so far we're doing good. We've deleted 66 outliers, we've fixed some missing data, we didn't have any typos. Now I'm going to move on to my actual assumptions. So normality, linearity, homogeneity, and homoscedasticity, the big four. Okay. You don't have to check these in any particular order, and they don't apply to every analysis, but generally they apply to most. I deleted some people, so I would need to rerun my analysis. But one thing I have on this handout, and it's part of the homework, is to look at univariate normality. Like I said, as we go, we're going to stop doing univariate, but this is just practice. And so for univariate normality, I'm going to look at skew and kurtosis. I'm actually going to run an analysis I ran at the very beginning, but this time I know there's no accuracy errors, I know there's no missing data that I could fix, and I know there are no outliers. So now I really want to look at it, because this is the point where I would do something about it. So I'm going to go Analyze, Descriptives, no frequencies. I'm going to pick my continuous variables. And then under statistics, I'm really just going to look for skew and kurtosis. I've already checked the means, checked the standard deviations, I've looked at the min and max, so now I'm going to focus on skew and kurtosis. And then under charts, I'm going to do histograms. I like the pictures. They're helpful. Okay, continue. Turn off all those frequency tables so you don't get 8,000 tables, and then hit OK. So I have include a box with skew and kurtosis studies. That would be this bad boy. And you can tell that I have done something because look, there's no missing data except for that one column that I knew was bad. And I would just look at the skew and kurtosis lines to make sure they're not over 3. So what's the cutoff scores for these to be non-normal? It's the absolute value of 3, so positive or negative 3. And I'm looking pretty good. Generally, if you don't have a problem in step 1 with skew and kurtosis, you're not suddenly going to create one in step 5. So if skew and kurtosis look okay at the beginning, they're usually okay at the end too. And then I can scroll through the pictures. Now clearly some of these are slightly skewed. Okay, it's only a 7-point scale. So if you look at this question 31, it's got a slight positive skew. And then question 33 has a slight negative skew. Again, it would help if I had reverse scored these because they should all have a slight negative skew. But they're looking okay. They're not super bad. So you'll notice this more as you have distributions with long tails on the end. If you're not good at seeing these, I tell you to make sure you add that normal curve. But the more of them you look at, the easier it gets. Why do they look kind of funky? Well, if you'll notice, the little bitty dots down here, this is a 1 to 7 scale. So the bars are the scores that people picked, and these little bitty spots down here are the numbers that we filled in. So that's why it looks kind of weird. It's because it has these little bars down here, and it couldn't collapse across those. So most of these are okay. You know, they're not perfect, but they're within our normal range. And so here's an example of one where we didn't fill anything in, so the bars are much closer together. Okay, so the difference between this death question and this one below it is that this one didn't have any missing data filled in, and this one's got some decimals, and that's okay. So none of our variables appear to be univariate problems. But I'm much more interested in the multivariate. So let's get a new set of multivariate data that we can use for points 5, 6, and 7 on this handout. Go to Analyze, Regression, and then Linear. I still have all this set up. I haven't closed SPSS, so my save option is still here with Mahalanobis. My plots, oops, wrong button. Plots are all still set up, so as long as you don't close SPSS, it'll leave this set up for you, which is nice. So I'm going to hit OK. Now, because I didn't turn off Mahalanobis, I will get new values out here, and they are going to be different because I've deleted people. Totally ignore them. Don't double screen for outliers. Don't delete people twice, just once, because we don't want to just keep chopping off the tail of people on the end. We just want to look at it once. Go back to my output here. I'm ignoring all this stuff at the front, and I just want the pictures. Okay, so ignore all the model summary, ANOVAs, and all that, because this is a fake regression, because we're just doing data screening. So this is the plot I would want for my multivariate normality histogram. So like on 5B, it says, include a multivariate normality histogram. This is the picture. It needs to say random up here to show me that you ran this as a random regression. And it needs to say regression standardized residual down here, showing me that you got the complete residuals chart and not just one variable. So what am I looking for here? Well, it should look normal, but if you're not good at this, look at the numbers along the bottom. So you want the majority of the data, most of where the heavy bar stuff is, to be between even numbers around 0. So 2 and 2, 3 and 3, 4 and 4. So you want it to be fairly even on each side of 0. And you want the tallest bars to be centered over 0. So I got most of the data here over around 0. I have a slight positive skew, but it's not bad. There's just a little bit of people out here. You will always have these little bit of people out here or over here. So we're looking for the majority of the data is between 2 and 2, and most of it's over 0. So I'm okay. Normality is the one you can break. If you've got at least 30 people, normalities just will kind of work itself out. So this is one of the most flexible assumptions, meaning that if you don't quite have normality, it'll still be okay, and that's called robust. So it's a very robust assumption, meaning you can kind of bend the rules. Now, for linearity, if I wanted to do a univariate chart, the easiest thing to do is called a scatter matrix. SPSS is a little cranky sometimes and doesn't want to run one for you, and so you can just do a couple variables at a time. But if you can't get a scatter matrix to run, these are scatter plots. And so in theory, univariate linearity is where you should have all of the combinations of the variables are linear. And that means like 1 and 2 are linear, 1 and 3, 1 and 4, 1 and 5. And so that's going to get really tedious if you have 200 variables, right? So Generally, people don't check for univariate linearity because that just takes too damn long. So I'm going to show you how to do a couple of them, but we won't do all of them because that takes forever. Now, the homework is only 3 questions. That's pretty easy. So let's create this scatter matrix. And that's going to be in the graphs window. So we're going to go graphs and then chart builder. And I'm going to click on scatter dot. And I have this scatter plot matrix option here. So I'm going to drag and drop that into the main window. And then generally 3, 4 is kind of your upper limit that it'll let you do at once before it just kind of goes and doesn't run. So I'm going to pick the top 3. So you can hold down Shift and click on the top 3. You can hold down Control and pick which ones you want. But you need to have all 3 selected. And then you're going to, oops, come on now. Okay, you got to hold down Shift to pick them. All right. All 3 of them. Oh, I'm having trouble today. There we go. And you're going to drag and drop until you get the red cross plus. And that means it's going to do more than one variable at once. So I'm going to put all 3 in there. You may be able to do a couple. Yeah. Okay, so in this analysis, you can drag and drop them one at a time. That's not always true, but in this one, you can move them over one at a time, or you can highlight the ones you want and do that. And now I'm just going to hit OK. There's no special windows because this is not something you would publish normally. And what it's going to do is give you some very crazy looking charts. And so it's the same thing as a correlation table where the top half and the bottom half are the same, they're just flipped. And what I really want to do is make sure that none of these look like little rainbows or bows and arrows. So you don't want anything with a bend in it. This data is mildly categorical, meaning it's like 1 or 2 or 3, so you will get these kind of super fun dot plots that don't look like anything. And with these plots, the darker dots mean there are more people stacked together there. So there are 1,500 dots in that, it's just they've stacked them on top of each other. And then our little out-of-line dots are our data that we filled in. And so mainly, I just don't want it to look curved. And when you see it, you'll see it. So you just do not want a curvilinear thing. Anything that looks like a chair or a rainbow or anything like that. So I would say no. Both of these look fine. None of my pairwise combinations, that's 2 variables at once, look bad. Now, because univariate linearity is so horribly tedious, most people do multivariate. And we already have that output. So I am going to go back up to my fake regression, and this is where the PP plot comes in. Don't ask me what it means because it's the normal probability plot, so there's an extra P in there somewhere, but it's called a PP plot. And I needed to, when you turn this in, to say dependent variables random, and it's the standardized residual plot. And linearity you can be pretty flexible on too. This one is fairly close to the line all the way throughout. And so just kind of squint at it. Does it look like a line? Yes or no? And so I would say yes, this indicates multivariate linearity. It looks pretty good. That's pretty close. And then the very last 2 is homogeneity and homoscedasticity. Now, there is no univariate version of this right now. When we get into running ANOVAs, we'll talk about Levine's test, and running MANOVA would be Box's test for homogeneity. And there's not really a homoscedasticity univariate one. So to me, this was just much easier to always check the multivariate. And for right now, that's the only option you have. So I want to look at this random scatter plot. So remember, the bottom is the residual. That's how different am I from a random variable, so that should be random. And the side here is the predicted value. So if I use all of my data to predict a random score, what am I getting? Which should also be random. So both on X and Y, I should just get a random smattering of dots. And generally, you want that to be centered around 0. So for this is going to be the multivariate residuals plot, is what you want to include for your homework. And so they interpret the graph part. For homogeneity, I want the dots to be centered around 0. So if I go across here and look at this line here, are most of the dots around 0? Is there an even spread? And again, if you're not looking at it, look here. So it's -4 to 4, which is perfectly even. Now there are more dots in the middle. That's kind of normal. And so there's a pretty even spread on top and bottom. Okay, so they will sort of sometimes cluster around the middle. That's okay. But what you don't want is it to be 2 to -6. That would be bad. Now let me look at it both directions here. So I'm going to go 0 from the bottom. And it's running 2 to 4, so not perfect. But you have to realize out here in 3 and 4 is just a little tail of people. It's very similar to the fact that in the normal chart, you get this little tail of people out here. That'll happen. So it's okay. It's from 2 to 4. That's all right. Now, after that is when it starts being bad. So when it starts to have like 3 or 4 points on one side that aren't on the other, that's going to be bad. Okay, so 2 to 4 is kind of the last push that you can have before you have to start going, oh, okay, what do I do now? Okay, so that's homogeneity. Homoscedasticity is a little harder. So you want the spread of the dots to be relatively even all the way across. So we had a student one semester who drew me pictures around these dots, but basically I want for the dots to look kind of like a blob. And so I would kind of draw an imaginary line here. Is there any missing data? Well, there's not really a whole lot out here on this right side because we have our little tail of people, but the majority of the data is fairly much just a big blob of dots. Okay, God bless one dude out here. There's always that one dude. And so I would say this looks all right because it doesn't appear to make a megaphone shape or a fish or a UFO. It appears pretty much like a circle. If you want to know who some of these little dudes are, you can double click on the graph and use the bullseye button here, so this bullseye, and click on the dot, and it will tell me what the line number is. So remember that is the line number in SPSS. So if I click on go back to the data, so 46, that would be line 46 out here. So it's telling me that this person is my very strange dot. So I might go and look at, like, why is their dot so strange? So most of their scores are pretty normal. All right, go back to the data here. So this would be the last graph I would look at. And again, I'm just kind of looking for a big blob here. So I would say that both of these appear to be homogeneic and homoscedastic. So heterogeneity and heteroscedasticity are bad. So with all of these, sometimes the questions get really awkward when I'm trying to ask you on the homework, does it work or not? And if you're not sure how to answer, just tell me what you think. So yes, the correlations look fine. Okay, so do you have multicollinearity? Well, the answer is no, but if you say the correlations look fine, then I know what you're trying to get at. For normality, do you meet normality? Yes. The graph runs from 2 to 2, and I know that you know what's going on. As we go throughout the semester, what we'll do is we'll start to just wheedle it down to just the multivariate options, and it'll get to be much more like, yes, I know I've met this. But for right now, tell me, yes, I've met this because. So I know that you're on the right track and that you're not just guessing. You might be guessing, but give me a reason why you're guessing, and then I can tell you if you're incorrect or not. But if you just write yes and no, you'll only get about half credit, because I want to know why do you think that you've either met the assumption or not. Okay. And so that is the end of data screening. Hopefully this will help. Let me know if you have any problems with the video or audio on this recording.